All right. Yeah. So my name is William Toledo. I'm a doctoral candidate at New Mexico State University, and today I'll be going over my research on the effects of substrate texture and moisture conditions on ultra high performance concrete overlay bond strength. Okay, so first off, I want to go over the objective of the study, and of course, it was to assess the effects of substrate texture and moisture conditions on ultra high performance concrete bond strength by use of a direct tension bond test. Okay, so this is the presentation outline. Of course, we went over the objective. Then we'll go into some background, which covers cementitious overlays, overlay bond strength, ultra high performance concrete. Then we'll go into experimental methods for this study, the results and discussion after that, and then finish off with some conclusions of the study. Okay, so first off, what is an overlay? It's just a popular deck repair strategy that protects steel reinforcement by providing extra cover as shown here in this illustration. And it can extend service life of existing bridge decks and can be a cost-effective alternative compared to full deck reconstruction. And overlay is just a repair strategy to rehabilitate deteriorated concrete bridge decks by providing a thin layer of repair concrete as shown in this illustration. Okay, some things to consider when considering an overlay material is the bond strength. So we need to assess bond strength because of a phenomenon called curling. And curling is just the upward or downward bending at the edges of the overlay material, usually caused by differences in moisture and or temperature between the overlay and substrate materials. So we get upward curling when we have low moisture or low temperature above the overlay and high temperature and high moisture below the overlay. And we get this upward curling, which can cause normal tensile stresses at the edges and shear stresses at the midspan. And we get the opposite, downward curling. Well, of course, we have the downward or the opposite, high moisture, high temperature above the overlay, low temperature and low moisture below the overlay in the substrate. You get this downward curling, which can cause normal tensile stresses at the midspan and shear stresses at the edges. Okay. So the overlay material used in this study is going to be an ultra high performance concrete or UHPC. UHPC is produced with fine materials, with the coarsest material being a fine sand passed through a number 4 sieve. UHPC exhibits compressive strengths of at least 17,000 psi and shows excellent durability against chemical and physical attacks. Has extremely low chloride ion permeability and shows little or no deterioration after being exposed to 300 cycles of freezing and thawing. When tested for abrasion resistance, had very little mass loss and has excellent density and low porosity, as well as excellent flexural strength, typically around 1500 to 2600 psi, and is ductile and fiber reinforced. Okay, so the typical composition of UHPC or the non-proprietary UHPC we developed at New Mexico State University. Of course, we have our type 1-2 cement, our fine sand that's passed through number 4 sieve, and we utilize supplementary cementitious materials to make up some of that cement content, which is made up of silica fume and fly ash. And typically for UHPC, we have a low water to cementitious materials ratio, typically around 0.13 to 0.16. And to use that low of a water to cementitious materials ratio, we need to implement high range water reducing admixtures or superplasticizers. In this case, we use BASF's master selenium 3030. And of course, to have UHPC, we need our high strength steel fibers. In this case, we have our needle fibers, which is 13 millimeters long, has a length to diameter ratio of 65. Okay, so now we want to go into the experimental methods of this study. First, going over the bond assessment test method, which is the in situ direct tension test. So we use this test to investigate substrate surface moisture condition and surface texture. So we made these specimens by first casting substrate concrete in a 6 by 6 by 24 inch beam mold at a depth of 4.5 inches, texturing that surface, and then overlaying it with a 1.5 inch thick UHPC overlay, as shown in this illustration. And we call this in situ direct tension test because we don't completely core out the specimen. So we core down 2 inches, so you pass the UHPC overlay and about 1/2 inch into the substrate concrete, as shown in this illustration. And our cores are with a diameter of 1.75 inches. So what we do is we epoxy these steel load plans onto the top and then use a field pull-off tester, as shown in this photograph, to perform the pull-off test. And this does provide a direct tension bond strength. Okay, and in the study, we want to perform tests on surface textures, specifically surface textures that provided a degree of aggregate exposure. So we used 5 surface textures, and as a beginning, we used the tine texture to mimic texture on a mop placement slab, which was produced 30 minutes after placing new substrate concrete. So it's produced in the fresh state, and is shown here, the first photograph. And as you can see, our surface base is intact and it provides a smooth surface. So we wanted to provide a degree of aggregate exposure. Therefore, we used ACI 303 to select 4 textures, 4 sandblasted textures: brush, light, medium, and heavy. So, and they're shown here. So the brush sandblasted texture partially exposes fine aggregate, and the light sandblasted texture exposes fine aggregate, and the medium sandblasted texture partially exposes coarse aggregate, and the heavy sandblasted texture exposes coarse aggregate. Okay, then we also want to investigate substrate surface moisture conditions prior to application of the UHC overlay. So we did this by allowing surfaces to dry for predetermined times before placement of the UHC overlay. And when we say we had a drying time of 0 minutes, that just means we maintain saturation up until application of that UHC overlay. As you can see, we still have freestanding water here. And what we did was allow these specimens to dry for these times, so 15, 30, 45, 60, and 120 minutes. And when we refer to the 120 minutes, we refer to the dry specimens. So, and vice versa. When we refer to the dry specimens, we're referring to this 120-minute dried specimen. And some things to note is that specimens allowed to dry for 45 minutes or less still had visible moisture. And the 45-minute case was the last case when we had visible moisture. Okay, so this research is broken up into 3 studies. The first being the extreme substrate surface moisture condition study, where we investigated dry and saturated specimens. Again, the dry was dried for 2 hours or 120 minutes, and saturated specimens were maintained saturated up until application of the UHC overlay. So they had visible moisture and freestanding moisture. Okay, so the dry specimens had a tined or heavy sandblasted texture, and the saturated specimens had a tined light sandblasted or a tined medium sandblasted surface texture. And we also wanted to investigate the surface moisture conditions between dry and saturated. So we performed the partially dried substrate surface moisture condition. And here we allowed the specimens to dry in ambient lab conditions for 15, 30, 45, or 60 minutes before placement of the UHC overlay. And it should be noted that the texture used for these specimens was a tined light sandblasted. We also want to investigate surface textures. We performed a surface texture study, which investigated degrees of aggregate exposure. This is where we used the ACI 303 to define those brush, light, medium, and heavy sandblasted textures. So here we use the substrate surfaces that were allowed to dry for 45 minutes because this was the last case when there was visible moisture. And of course, the textures range from tined brush sandblasted to tined heavy sandblasted. Okay. Okay, so now we want to go into the results and discussion of this study by first going over the overlay material characterization and the substrate material characterization. First being the UHC characterization. So we did have a thixotropic UHC mixture. So thixotropic just means it's very viscous at rest and won't move until energy is put in to move that mixture. So we want a thixotropic mixture because we have no control of where we place this UHC. So if we place on a slope surface, we don't want that UHC just to run off. We want to be still until energy is put in to move it by using a vibrating wand or a vibrating streak. Okay. And this is the mixture proportions for that UHC mixture. 80% is made up of cement. 80% of that cement content is made up of type 1-2 cement. 20% is made up of supplementary cementitious materials, which is 62.5% is made of the silica fume, and 37.5% is made up of that fly ash. And our steel content is 1.75% by volume for that. Okay, so this mixture did provide adequate workability with a slump of 5 1/4 inches and a flow of 9 3/4 inches. And we did achieve the minimum ASTM C1856 compressive strength of 17,000 PSI for UHPC with a 28-day compressive strength of 17,270 PSI. Okay, and here's the substrate concrete characterization results for the, of course, the substrate concrete. So the substrate concrete was a normal strength concrete with a 0.4 water to cement ratio. And this mixture was designed to have a slump of 2 to 3 inches and an air content of 5%. And we had a 20-day compressive strength of 6,600 PSI and had the following mixture proportions. And of course, this was an air entrained concrete, so we used air entraining admixture for this. Okay, so now I want to go over the in situ direct tension bond assessment test results. So first off, we're going over the substrate surface moisture conditions prior to placement of the HPC overlay. So these are the specimens we allowed to dry from saturated conditions for predetermined times. So a little thing about the plot, we have these, so this dotted line is going to be ACI 546 good bond strength of 150 PSI, and the solid line is going to be ACI 546 excellent bond strength of 250 PSI. And as you can see, specimens allowed to dry for 15 or 30 minutes were able to exceed that 250 PSI recommendation. And specimens that were visibly moist, specimens that were dried for 45 minutes or less, were able to exceed that 150 PSI minimum recommendation for adequate bond strength. And specimens that were allowed to dry for 60 or more minutes did not achieve that adequate bond strengths, not even close to achieving it. And it should be noted that the specimen here for comparison is the exposed aggregate specimen. And this is the ideal case to have an exposed aggregate texture prior to UHPC overlay. However, by not maintaining saturated conditions, we did not achieve that, we didn't achieve any bond. So we got 0 bond strength for those ones. Okay, so the next one is the substrate surface texture. So we still have the same ACI recommendations, the minimum or the good bond strength and excellent bond strength. For comparison, we use the tined specimen with the saturated conditions, and saturated conditions is the ideal case. To maintain saturated conditions until application of the HPC overlay is the ideal case. However, by not removing any of that surface paste from that tined texture, remember it was a smooth surface with the surface paste intact, we did not achieve that adequate bond strength of 150 PSI on average. But by partially exposing that fine aggregate and removing that surface paste, we're able to exceed that 150 PSI recommendation. And by exposing more aggregate, we're able to achieve more strength. And by partially exposing coarse aggregate and exposing coarse aggregate, we're able to exceed that 250 PSI recommendation on average. So whenever using the UHPC overlay, we need to make sure we're able to provide a surface moisture conditions that is visibly moist at application of the UHPC overlay, and provide a surface texture that at a minimum partially exposes fine aggregate and removes that surface paste to achieve adequate bond strengths. Okay, some conclusions from this study. UHPC overlay did not develop bond when the substrate surface was allowed to dry prior to overlay placement. Adequate bond strengths were achieved as long as the substrate surface was visibly moist. Textures with increasing amounts of aggregate exposure provided increased bond strengths when the substrate surface was properly saturated prior to overlay placement. And saturation of the substrate surface is important for developing adequate bond strengths. And again, that adequate bond strength is 150 PSI at 7 days, set by ACI 546. And lastly, slightly inadequate bond strengths were observed under wet conditions when no effort was made to remove surface paste from that tined texture. Okay, that concludes my talk, and ready for questions. Thank you.
Thank you, Toledo. I haven't seen any questions in the chat box. So let me start one. I guess when using UHPC for overlay, are you aware of any challenges on site? I mean, in terms of constructability?
Yeah, well, I think the most challenge is getting an adequate amount or volume of UHPC to maintain construction. Because right now to mix the UHPC, we use a pan mixer, and when we use high velocity pan mixer, we need to utilize a lot of them just to make sure construction keeps going.